Welcome back to an introduction to real analysis, concluding chapter 4 with section 4, the inverse function theorem. Suppose you have f of x equals ax, where a is non-zero. This is an invertible function, and it's quite easy to invert. The inverse function is x over a. So what's the derivative of f? It is simply a. What's the derivative of the inverse? 1 over a. So we end up with this interesting identity that the inverse function's derivative is 1 over the derivative of the original function. Now this was for the very simple example of f of x being ax. Now since a differentiable function is almost a straight line, is this true in general? Yeah, actually it is, provided we properly define what f of x equals y represents here. So here's a lemma. Suppose I and j are intervals. Suppose f maps I to j and is strictly monotone one way or the other. It's surjective and there is some x naught where f is differentiable and the derivative is non-zero. Then the inverse function is differentiable at y naught defined to be f of x naught, and the inverse function derivative at y naught is the reciprocal of the derivative of f at x naught. In other words, it's exactly what we observed with straight lines under suitable hypotheses. So since f is assumed to be strictly monotone, the inverse does exist. It's a surjective, strictly monotone function, so it's injective and surjective. It has an inverse. We've already shown that in this case, because we are mapping an interval to an interval with a strictly monotone function, f inverse must be continuous. So denote this inverse as g mapping j to I. Let's let x naught be a point in I and y naught be f of x naught. In general, just let y be f of x. Whatever x is in I and y is in j, this is our relationship between x's and y's. Now, if x is not equal to x naught, then since f was strictly monotone, f of x is not equal to f of x naught. In other words, y is not equal to y naught. So let's work through this difference quotient. G, the inverse function, g of y minus g of y naught over y minus y naught. Well, that's g of f of x minus g of f of x naught over f of x minus f of x naught. But what is g of f of x? They're inverses, so that's x minus x naught. So we've just established this kind of reciprocal identity between g and f. So let's define capital Q. This is going to look very similar if you think back to the proof of the mean value theorem. Define capital Q as this quotient that we just derived up here, at least wherever x is not equal to x naught. If x is equal to x naught, let's make it exactly 1 over f prime of x naught. F is differentiable at x naught, and f prime of x naught was not 0. Meaning, if you take the limit as x approaches x naught, this is exactly the reciprocal of the difference quotient of f. Since we're not getting a 1 over 0, the limit as x approaches x naught of this will be exactly this value here. In other words, capital Q is continuous at x naught. So since g is continuous at y naught, the inverse function, okay, it was continuous, so the composition q of g is continuous at y naught. All right, so here was our function q, and we observed that q of g will be continuous at y naught. Now let's work through the derivative of f inverse at y naught. Now f inverse is what we call g, so this is the limit as y approaches y naught of this difference quotient. All right, what's q of g of y? Letting x be g of y, you get g of y minus g of y naught over f of g of y. But f and g are inverses, so that would just be y minus y naught. So this right here is exactly q of g. We're now taking the limit as y approaches y naught of q of g, which is continuous at y naught, so just plug in the value y naught. What is g of y naught? It's x naught. So q of g of y naught is q of x naught. What's q of x naught? Because it's continuous, 1 over f prime of x naught. So what have we shown? The inverse function derivative at y naught is 1 over the derivative of the original function at x naught. Now, if we further assume that the function f has a derivative and is continuous and is non-zero everywhere, then what follows is that for all points in j where y is equal to f of x, The derivative of the inverse function at y is 1 over the derivative of the original function at x. Since f prime is continuous and non-zero, this is now just the reciprocal of this, meaning this is continuous and non-zero as well. So now we can state and prove the inverse function theorem. Suppose f is continuously differentiable and the derivative is never zero on an interval from a to b, an open interval. Then there is an open subinterval I containing x naught so that the restriction to I is injective and has a continuously differentiable inverse g, such that you end up with the appropriate relation between the derivative of the inverse function g and the reciprocal of the derivative of the original function f. Okay, let's prove it. Without lots of generality, let's assume f prime at x naught is positive. We've assumed f prime at x naught isn't zero, so if it happens to be negative, multiply by -1, whatever. Since f prime was continuous by assumption, and at x naught it is positive, again citing exercise 3.2.11, there is in fact an entire interval around x naught where the derivative is positive. Great. Since the derivative is strictly positive on this interval, the original function f is strictly increasing. We therefore have a bijection between I and f of I because it is a strictly increasing function. But we assumed f was continuous. So by corollary 3.6.3, f of I must be another interval. Now lemma 4.4.1 kicks in because we now have an interval being mapped to an interval by a strictly monotone function that has a derivative that is continuous, etc., and we're done. In example 123, we showed that there was a unique positive real number whose square was equal to 2. We denoted it as root 2. Then later in section 3.3, we used the intermediate value theorem to show that positive numbers have roots in general. But now we can show there is a unique non-negative root. We can therefore define the unique non-negative nth root of a positive number x. We're going to call that x to the 1 over n. So let n be a natural number, let x be non-negative. There is a unique non-negative y, so that y to the n is equal to x. We will therefore call y the nth root of x, or x to the 1 over n. Furthermore, this function, g of x given by the nth root of x, is a continuously differentiable function whose derivative follows the form that you would expect. So we can prove this. At x equals 0, the unique solution is quite trivial to find. So let's restrict ourselves to positive values of x and look at the function f of x equals x to the n. This is a continuously differentiable function. Its derivative is n times x to the n minus 1. And the derivative is positive, so f is a strictly increasing and therefore injective function. Furthermore, x to the n is bigger than or equal to x, so the function is not bounded above. Since the limit as x approaches 0 from above of f of x is 0, the function f maps 0 infinity to 0 infinity in a bijective manner. Now let's let g be the inverse function. Because we have a bijective map f, it has an inverse. So let g be that inverse. We now have a unique non-negative root. And in fact, because we have excluded 0 here, for positive x's, there is a unique positive nth root of x, given by this inverse function. Okay, since this function g is the inverse of f, we can call on that previous lemma. The derivative of g at x is 1 over the derivative of f at g of x. G of x was the nth root of x. F of x was x to the n, so its derivative is n times the input to the n minus 1 power. And now just based on laws of exponents, we arrive at the desired form here. Now I'll mention, we've been a little glib here. This was our unique non-negative nth root of the non-negative number x, and we just cited that laws of exponents work as we expect. We haven't formally proven that. It's a bit laborious, but not especially difficult to show that they work just fine. Okay, so this last computation is tedious to actually go through step by step and show that everything does what you want it to. So I'll just say it's left as an exercise. Let's take a look at another example. So the previous corollary gives a good example of where the inverse function gives us a smaller interval than ab. So consider the function x squared. f prime of x is non-zero as long as you are not talking about x equals 0. So an inverse can be taken on any interval which doesn't include x equals 0. Now the convention is to define this inverse function on the interval from 0 to infinity. Then you continuously extend it by setting root 0 equals 0. As another example, consider the cube function f of x equals x cubed. Now we have a bijective mapping from R to R, so we can define the inverse function on the entire real line. Now the function f has a continuous derivative, but the derivative is 0 at x equals 0. So the inverse function has no derivative at x equals 0. Okay, the derivative exists everywhere else, but at places where the original function f has a 0 derivative, the inverse function theorem is not going to apply. And if you attempt to manually compute the derivative of the cube root function at x equals 0, you'll see that it doesn't actually exist there. Okay, here is the plot of the cube root function. And you'll see that it doesn't have a nice tangent slope at the origin. Because the original function has a flat slope at the origin, the inverse function has a vertical slope. Computing out the derivative, you'll see that this limit fails to exist. You can also see exercise 4.4.4. Okay, let's go over this rather short section. The inverse function theorem is going to be useful to us, but it's something we're going to cite in the background. Specifically, later in section 5.4, we're going to quickly derive properties of exponential functions because we will have already rigorously defined logarithms. Then exponentials are defined as their inverses, and then we just cite this and get some properties of exponential functions out of it. Also, we've used the inverse function theorem to work through how exponential functions honestly should be defined to begin with. A bit of kind of background noise that generally is not presented, especially at the undergraduate level.